This is the next video in the chapter on chemical bonding and molecular geometry. We just learned to use Lewis symbols to represent ionic bonding. So now we're going to introduce the octet rule so we can use Lewis symbols for covalent bonding. So our octet rule will probably sound familiar. This is basically the noble gas configuration rule that every atom is trying to obtain a noble gas configuration. We'll spell it out. So the octet rule says that main group atoms, those in groups 1 and 2 and 13 through 18, they will tend to give, take, or share their electrons until each atom has 8 valence electrons. I.e. a noble gas configuration. Every atom's goal is to have the same electron configuration as a noble gas, where it's the most stable. There we are. So this is most important here for covalent bonding. So let's grab a couple of examples. I'm going to use the halogens. So I'm going to use a small one, fluorine, and a larger one, bromine, to obtain an electron configuration of a noble gas. These elements form anions. They gain an electron. So fluorine's configuration looks like helium, 2s2, 2p6, or we could write it as neon if you wanted. And we can see the 8 valence electrons, or the octet, here in the highest principal quantum number, s and p orbitals. Bromine is a little bit larger. It's way down here in the 4th period, and so it's 3d orbital. The first d orbital is also filled for this guy. So its configuration looks like argon, 4s2, 3d10, or p6, which is the same as krypton. And in this case, the 8 valence electrons are the 4s orbital and the 4p orbital. Technically, the d and f electrons don't count as valence electrons because they don't have the highest principal quantum number. They're not in the 4th shell. Only the 4s and the 4p are in the 4th shell. So we're trying to gain 8 valence electrons. The only 2 elements that don't wish to gain 8 valence electrons are the ones that are too small to hold 8. And those are hydrogen and helium. Hydrogen and helium only have a first shell, and that first shell only has a 1s orbital in it, and the 1s orbital can only hold 2 electrons. So these guys only need 2 valence electrons, which you can call a duet instead of an octet. They are just simply too small to hold 8 valence electrons. All right, so let's put this new tool, the octet rule, into action and look at covalent bonding. Do some sharing. All right, so we'll do the same one that we did the first time we introduced covalent bonding, which is bonding 2 chlorine atoms together. So remember the electron configuration of chlorine. Chlorine has 7 valence electrons. So I'm going to do the left one in red and the right one in black just this first time so we can watch. And remember what we said when we talked about bonding, how these guys are both nonmetals. So neither of them is going to be able to steal an electron from the other. Instead, each of the chlorines is going to give one of its electrons to be shared with the other. So they both have 7 valence electrons, and they wish to have 8. So they will share 1 with the other one to give Cl2. So we've got 1, 2, 3, 4, 5, 6. The 7th is in the middle. And 1, 2, 3, 4, 5, 6 red. The 7th is in the middle. And so these 2 electrons on the middle are the ones that are shared. And so we have special names for the electrons that are shared versus the electrons that are not. So these shared electrons that we draw in between the 2 atoms, this is called a bonding pair of electrons, because this is what forms the bond that holds these 2 atoms together. And then some of these other electrons only belong to one atom or the other, like this one. So this pair of electrons that belongs to one single atom alone is called a lone pair of electrons. It is not shared, it only belongs to this particular chlorine atom. And now that we've shared, this chlorine on the left has these 6 lone pair electrons, and it has 2 bonding pair electrons, so it has 8 valence electrons now, and so does this chlorine over here. And so we have complete octets for both of them. We can check those off. Now, I think that drawing the dots around each of these atoms really starts to become tiresome. And when you write it in pencil, especially, it starts to become difficult to see the dots if you don't make them large enough. So we're going to introduce a shorthand way of drawing this so that you can move a little faster when you're reading it and you can make a clearer written structure. We can draw these structures faster by drawing a line for each pair of electrons. We're going to start counting by 2s instead of counting by 1s. Then we can count faster. Just need to make sure that you count carefully. So if I wanted to draw Cl2 in this faster style of drawing, we're going to use one line for each pair of electrons. So let's look here. There's one bonding pair of 2 electrons. So we'll draw one line connecting those 2. Each of the 2 chlorines has 3 lone pairs or 6 electrons. So we have 2, 4, 6 electrons on the left chlorine and 2, 4, 6 electrons on the right. You can sort of think about it as having 1 electron at each end of the line, if that helps you to remember, or if it's really too much, you can always just draw the dots. But at some point it will start to become too much. And so every time we draw a molecule, we want to make sure that each atom has a complete octet, that it has 8 valence electrons associated. So with the lines, we can count 1, 2, 3, 4, 5, 6, and 2 shared, 7, 8. Check. And the same over here. 1, 2, 3, 4, 5, 6, and 2 shared, 7, 8. Check. So when I mark the check, what I'm noting is that the atoms with the check have a complete octet. Every time we draw a structure, we're going to check and make sure that they have a complete octet or a duet for hydrogen and for helium. So these are the simplest possible covalent structures we can do. Let's make this a little bit harder. Let's put more atoms in our molecule. Because sometimes there are more than 2 atoms in a particular structure. Sometimes one atom may need to share multiple electrons with multiple atoms. In order to complete its octet. And that probably makes sense, right? Chlorine has 7 out of 8 valence electrons. It only needs 1 more, so it only needs to share with 1 other molecule. But what if we had something like carbon? Carbon is in group 14. It only has 4 valence electrons. So it's unlikely it's going to find one atom that's willing to share 4 electrons at once with it. So what it's going to need is one atom to share each of those missing electrons that it needs. And we can do that in the molecule CCl4. So our other atom is going to be the chlorine, that same one as the one we had up here. And then we are going to draw a different color for the last time. Chlorine has 7 valence electrons. So when we make this structure, carbon is going to be sharing with all 4 of the chlorines. So carbon is going to have 4 electrons. It's going to share 1 with each chlorine. And each of the chlorines is going to have 6 lone pair electrons and 1 bonding electron shared with that carbon. You can see why I don't like making the dots. There are so many dots. There we are. And we can make sure, and we count to make sure each atom has a complete octet. 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And don't forget the carbon in the center. 1, 2, 3, 4, 5, 6, 7, 8 for carbon. And it's much easier if we draw that structure in the shorthand with the lines instead. Much less crowded diagram. So we have 1 line for each pair of electrons in the bonding pairs and 1 line for each of the lone pairs around these chlorines. And we can count and make sure the octet is filled, remembering to count 2 electrons for each line. So 2, 4, 6, 8 for this chlorine, 2, 4, 6, 8 for this chlorine. For the carbon in the center, 2, 4, 6, 8. All of those are bonding pairs. 2, 4, 6, 8 for the left chlorine, 2, 4, 6, 8 for the bottom chlorine. And so each of these bonding pairs, either drawn as a pair of dots or as a line, these can also be called single bonds. There's 1 pair of electron in each single bond. And I call that a single bond because we are about to introduce multiple bonds, when there are many shared electrons in between 2 atoms. Okay, so sometimes 2 atoms may need to share more than 1 pair of electrons. They need to share more than 1 pair of electrons to complete their octets. Sometimes there's only 1 other atom available, and you take what you can get. So in this case, carbon could bond to 4 different chlorines in order to get the 4 valence electrons it was missing. Sometimes you have to donate or share more than 1. So here's an example, C2H4. We can draw like this. And we can give 1 electron from the hydrogen and 1 electron from the carbon in this bonding pair, and the other 3 that are just like it. And so carbon has used 1 of its own and 2 of its own. It has 2 left, and it gives both of those electrons into bonding in the center and 2 electrons from the other one. So now there are 2 bonding pairs, and so we call that a double bond. And we can draw this in the shorthand notation. We can use lines, one line for each bond. So when we draw two lines, that represents a double bond. And single line, like we draw over here for the carbon-hydrogen bonds, are single bonds. So we have single bonds, we have double bonds, we also have triple bonds that are seen fairly commonly. You can see them in a molecule of carbon monoxide, where each of the carbon and oxygen atoms has a single lone pair, and there are 3 bonding pairs. Also drawn like this, 3 bonding pairs, 1 lone pair each. Call that a triple bond. So these are all the tools you'll need to represent individual Lewis symbols and how to put them together. And now that we have all the tools we need to put them together, in the next video, we'll talk about how to draw full Lewis structures from scratch.